Do you have a pen? Hey everyone, we just started the Zoom so that, well, the Zoom and the YouTube just so that people can filter in. I see a question in the chat about going over intensive versus extensive again. The way that I think about it is to just remember which one is which. Extensive has the word extent in it, and extent means amount. So that means that an extensive property depends on the amount of stuff that we have. So kind of the go-to example of an extensive property is mass. So just think about a pile of sand, and if I have more sand, then I have more mass of sand. So the mass of the sand that's in front of me is dependent on how much sand I have. If I have 1 grain of sand, that's going to have a different mass than if I have 1,000,000 grains of sand. An intensive property doesn't depend on how much sand I have in front of me. So color, if I have an entire beach or only a bucket full of sand, the color of the sand is still tan. Density is another intensive property because it doesn't depend on how much stuff I have. The density of sand is how much it weighs per volume. So the density of water, for example, is 1 gram per milliliter, where a milliliter is a unit of volume. So if I have 1 liter of water, it weighs 1 kilogram, and its density is 1 gram per milliliter. If I only have 1 milliliter of water, its mass is 1 gram. So its mass has changed now that I have less water in front of me. Whereas its density is still 1 gram per milliliter. So the density is an intensive property because it doesn't depend on how much stuff I have, whereas the mass is an extensive property because it changes depending on how much stuff I have. So whenever you're asked if something is intensive versus extensive, just ask yourself, if I double the amount of this substance that I have, will this property change? The mass will change, the density will not, the color will not. I hope that helps. Follow up if it doesn't. I'm happy to explain it more. You're also welcome to stay after class and we can have a discussion without a 20-second lag about what in particular is confusing.
How many participants? How many people are in?
There are currently 44 people watching. So there's a difference between the property you're looking at and the substance itself. So color is a property of a substance. So you shouldn't be thinking of, am I adding more color to something? You should be thinking of, I'm adding more of this substance. Is the color changing? So kind of what I am changing is just the amount of the actual substance I'm investigating. So water or sand or diamonds or whatever. And that's what we're changing. And then what we're looking at is, does our property change? So color is the property, not the substance. So if I change the amount of sand I have, the color doesn't change. We're not saying, if I add more color, what happens? Color is the thing that we're measuring. So if you think of dependent and independent variables, the independent variable is how much stuff do I have, how much sand or how much water do I have, And then what's changing, what we're looking at as our dependent variable is the property. So does the color change when I change the amount? If yes, then color would be an extensive property. But it doesn't if I have one blue shirt or 10 blue shirts, they're just as blue. So color is an intensive property. As more people are filtering in, we're gonna start in just a minute. I was just answering some questions before we get started. I see that there are about 60 of you now, so maybe we'll wait just a couple minutes to try to get everybody in the room. I see a question about the problem set. We're not going to go over the answers to the problem sets in class, just in the interest of time. We want to keep the actual in-class lecture focused on the sort of new material, but we will post the solutions on B courses, probably right after class. So those written out solutions will be available. And then you're welcome to ask us or the tutors in office hours to go over a specific problem if you've looked at the solution and you're not sure why the answer is what it is. There are currently 74 watching in the Zoom. The link to the Zoom is the same as it was yesterday. So if you had it yesterday, then you should be able to get into it today. It's also on the B courses page. It's in a few places. If you look under announcements, it's in one of the announcements. There's also an instructions for connecting online document. It's also in the syllabus. So whichever of those is easiest for you to find. Should be in a few places. Also, before we get started, I want to thank everyone for being so active in the YouTube live chat. It really helps us. We really appreciate you all asking questions. It's a super important habit for you to get into in your classes. I think one of the biggest barriers to people is to people succeeding early on in classes is, and I did it too, is I have this tendency to think like, if I have this question, it's because I wasn't paying attention. And that is not the case. Chances are we've explained things poorly. And you should sort of keep that attitude that, you've been paying attention and your question is valid. And we really appreciate you guys participating and asking questions. Really helps us. Katie, someone asked if problem set 2 is up on B courses.
It is.
Okay.
Yeah, it's under the assignments.
Problem set 2 should be under assignments on B courses. So there should be an assignment, and then there should also be a file if you go to files. If you're still having trouble finding it, let us know. Do you want to get started, Key?
Yeah. There's more popping inside.
So someone's saying there's no PDF of the questions within the assignment on B courses. I'll go check that right now, but it should at least be under
It is on files.
files. So if you go to on B courses, go to files. It's in there, and I'll make sure it's added in the actual assignment. Sorry about that. Okay, so the problem set 2 file was already under files on B courses, but it is now also attached to the assignment.
Okay, hi everyone. So for day 2, we're gonna continue talking about some of the mass and energy topics that we left off from last class. So first off, we wanted to talk a bit about energy and why it's necessary to learn about in the context of chemistry. So as we learned yesterday, chemistry is all about chemical changes, and often these chemical changes are accompanied by changes in energy. So if you look at this picture of a fire that came out of a chemical reaction, it's pretty clear that energy has a pretty important role in how this occurred. So what actually is energy? Energy is broadly defined as the capacity to do work. And when we think of work, we can define work as the motion against an opposing force. Broadly, we can kind of break energy down into 3 separate categories: kinetic energy, potential energy, and electromagnetic energy. So first off, I wanted to quickly review what different types of energies are in each of these 3 categories. So starting off with kinetic energy. Again, this is a broad category, and there are several different subsets of energy in this category. So the first and most obvious, we can think of macroscopically moving objects. For example, if you're driving your car down the highway, your car has a certain velocity. And then we can use the equation for kinetic energy to calculate the energy of the car. So this would be 1/2 times the mass times the velocity squared. However, there's also other kinds of kinetic energy. So one of the other common ones is called thermal energy, or also kind of colloquially called heat. So this is energy due to the motion of molecules that we can't see with our eyes, but they are in fact all moving. So macroscopically, we observe thermal energy as temperature. But if we think about what this means on the molecular level, this is really just a bunch of molecules bumping around and moving. And since these molecules are all moving, thermal energy is considered a type of kinetic energy. So one of the other main categories is potential energy. Okay, so I see a question in the chat about what are the units. So we'll talk about units later in the class and in the practice problem they come up. But energy has units of joules. So one of the most common ways that we can store potential energy is through gravity. So we're all pretty familiar with gravitational potential energy. If you pick up an object and you let go of it, it will fall to the ground under the force of gravity. So this equation you can represent as mass times the acceleration due to gravity times the height that the object was above the ground. Another form of potential energy is Coulombic potential energy. So this potential energy is from the attractive and repulsive forces between charged particles. So this equation I have shown right below, that's the energy equals the charge of the first object times the charge of the second object divided by several constants and the distance between these two charges. The third type of energy is electromagnetic energy. So this is energy that's carried by electromagnetic fields. For example, when we listen to the radio in our cars, that's actually a form of energy that's carried by radio waves. So here I've shown the spectrum of all the different waves so that you can see that at different wavelengths of the waves, there's different values of energy. So waves are actually pretty complex and they're really important in chemistry, and we'll be discussing them a lot in a lot more detail in week 3, but this is just a general overview. So now we wanted everyone in their breakout rooms to work on this quick practice question. So if you have any questions in the chat, please post on the YouTube live stream because we can't see your questions in the individual Zoom breakout rooms. So it's helpful for everyone if they're all posted in the Zoom. But what we want you to think about in your groups is to use the equation for Coulombic energy and calculate how much energy there is between these two charged particles. And then we want you to quickly sketch a plot of this energy as a function of radius r. And then think about what is the limit of energy as r approaches 0, and what is the limit of energy as r approaches infinity. So we'll give you about 5 to 10 minutes, and then we'll check in again to see if anyone needs any help.
And make sure that you have accepted your invitations to breakout rooms. So there's maybe about 6 people who are still in the main Zoom room. So you all should have gotten invitations to join breakout rooms. So make sure you join those rooms and then discuss this problem in those breakout rooms. Excellent.
How are you guys doing? Please let us know in the chat if you need more time. Otherwise, we can go ahead and get started in a minute.
Okay, seems like a lot of groups need more time, which is really good to know, so we'll give you a few more minutes. Thanks again for putting feedback into the chat. We really appreciate it. There's a question in the chat about the sign of energy and whether it can be negative. Katie will talk about that when she's going through the solution to this problem. It's a good question.
How are you guys doing on time now? Do you still need more time? Just quickly let us know in the YouTube chat, otherwise we'll start reviewing the answers. Okay, everyone, we'll give you 2 more minutes and then we'll get started going over the answer just so that we have enough time in class to cover other material. But if you have issues with this question that we can't resolve, definitely feel free to stay after class and we can go over with it, with it again.
Okay, so just about 30 more seconds. Start wrapping up your thoughts, and then we'll come back together.
Okay, great. So we're going to go ahead and go over some of the answers. Again, if you're not finished, that's okay. Just follow along, and hopefully people in your breakout room can also help you too. Okay, so to calculate the energy for a +1 coulomb charge that is away from a -1 coulomb charge, we would use the energy for the coulombic potential. So here I have written out what that means in terms of the different units that you would use. And the answer you would get is -6 times 10 to the 11th joules. So someone in the chat had asked, can energy be negative? And the answer is yes. Energy can be positive or negative. And when we move on to the course, we'll start thinking about what this means in terms of stability and bonding. But for right now, it's just important to realize that the plus and minus on the charges does matter quite a bit, and you want to always keep track of those positive and negative signs. So you can also make a plot of the energy as a function of the radius. So this is the plot of this function as a function of different values of r. So this is basically a 1 over x type function. So you see that it has these two asymptotes to it. Yeah, that answer is rounded. So it's rounded to two significant figures. So if you write it out, I think it's 5.8 or 9. Yeah, so if you look at this graph, you can see that as r approaches infinity, energy approaches 0. And on the other side, as r approaches 0, the energy approaches negative infinity. So it's really good to keep in mind when we discuss bonding later in the class, because these repulsive and attractive interactions actually are really important for how bonding works in chemistry. So that's a bit advanced right now, but that's something good to have as your lookout for the future. Yeah, so someone asked to go back to the previous screen. So this, again, is the answer. So all of these are also going to be posted after class. And I do apologize for not putting joules at the end of my answer for energy. Definitely if I put that on an exam, I would lose some points because units are very, very important. But yeah. It's 10 to the minus 12th, yes. Yeah, so this is the graph. We'll show you later in class how to make fancy graphs like this without having to use Excel or anything complicated. So I got this from a program on the internet where I just had to type in the equation and then it made the plot for me. So we will do that later, we promise. Okay. So quickly, we also want to talk about the law of conservation of energy. So the total energy of a system can be found by summing up all sources of energy. For example, if you have kinetic energy sources, you have potential energy, and then you also have the electromagnetic energy. So you can add all of these different contributions together to get the total energy of your system. But also, energy cannot be created or destroyed. This is sort of a fundamental law of the way the universe works. And so because of this, we call energy a conserved quantity. So this is really good to keep in mind moving forward. Okay. So now we have like a quick break, but since we're running a bit behind, let's only take like a 2-minute break this time, but feel free to chat in your break rooms with each other, and then we'll move on to talking about dimensional analysis and significant figures and units.
And also just to add, for those of you who might have been a little bit confused about that graph or sort of what limits mean, like what happens as we get r gets really close to 0 or really close to infinity, that's okay. We know that that's a new topic. So we mostly just wanted to like give you practice working with energy, but if you're a little confused about that particular detail of it with the limits, that's okay. Don't panic.
Yeah, we can talk about it later, and you'll be getting some of that information in your math courses. So you don't need to know what a limit is, just think about where that function is moving towards, and we can happy to chat about that later.
Okay, so in just about 30 seconds, I'll move on to the next part of the course. So the next thing we wanted to talk about is units. So someone asked a really great question in the YouTube chat on the energy part of it, of what are the units of energy. And it's always really important to be asking that question. So if you're running a reaction and you ask me, how much water does this reaction need? And I say 3, that doesn't mean anything. That could be 3 liters, 3 grams, 3 tons. Or, you can think of it as you're cooking. If someone says you need to add 2 sugar, like is that 2 tablespoons, 2 cups? So it's always really important to put units on your measurements and on your answers. So on a test, if you ever write that the answer is just 5, at least in the engineering classes I've been in, you'll lose a point every single time. So that's a good habit to get in. In science, we have a system of agreed upon units. So that's just so that as we all do our different experiments, we're all reporting our units the same. So I'm not putting mass in pounds while Katie's putting it in kilograms. And if we did that, that would just add an extra step for everyone and be confusing. So basically, these SI units are the agreed upon units. So for example, for mass, that unit could be kilograms or pounds or grams or tons or any number of things. So in the YouTube chat, just type in what your guess would be for what the SI units are for these quantities. So mass, length, time, temperature, the amount of substance, and it gets a little tricky, electric current and luminous intensity. I will be totally shocked if anyone gets the units for luminous intensity right. I had to look it up. So yeah, just to sort of get a feel for what you think some of these SI units might be. So you can just throw in, if you know one of them but not the others, just throw in whatever units you can think of that might be the SI units. Cool, so we have grams and kilograms as guesses for mass. I see Celsius, I see meters, I see moles, that's great. Yep, that is, spoiler alert, that's right. See if any more come in. Lumens, grams, meters, seconds, ohms. I see joules, kilograms, Kelvin, kilojoules, Celsius. So you have a couple options for temperature that have been in there, Kelvin and Celsius. I see meters, amps, yeah, seconds. I see minutes, and now I see Fahrenheit for temperature. That's another unit of temperature for sure. Okay, these are all great suggestions. I'm just going to keep going. You all have put in a sort of wide variety of units. And this kind of illustrates why it's important that we have SI units, because if we're all writing papers where some of us have units in Celsius, some have Kelvin, some have Fahrenheit, that can be really confusing. So it's best if we all sort of agree on what units we're generally going to use. So the SI units are kilograms for mass, meters for length, seconds for time, Kelvin for temperature, moles for amount of substance, ampere or amp, so someone got that one, for electric current. And then yeah, the unit for luminous intensity is the candela. So that's your fun trivia fact for the day that I definitely didn't know a week ago, so you definitely shouldn't feel bad if you didn't either. So just kind of keep these units in the back of your head as sort of a default of if you're not sure what units you should convert into, these are always a good bet. That doesn't necessarily mean that you always have to convert into SI units on every test, but you definitely should be comfortable with these units, not the candela and maybe not the ampere yet until you get farther into physics, but kilograms, meters, seconds, Kelvin, and moles, and we'll talk about moles more later in the week. But yeah, so there's those first four we're going to try to get you familiar with now if you're not already, and then we'll get to moles in a couple days. So how do you actually convert between units? So you would need to do this if you're given something in non-SI units and need to convert into SI units, or vice versa. So maybe you only have a scale that measures things in pounds, but your equation requires mass in kilograms. So there are conversion factors that do that. So for example, 1 mile is 1609.3 meters, 1 minute is 30 seconds, 1 day is 24 hours. There's a whole bunch of these conversion factors. And then the other thing you might need is if the order of magnitude that you're working with. So that just means if I'm talking about the mass of planet Earth, using it in kilograms is going to be really annoying. That's going to be a really, really, really big number. And so what we do in that case is we use prefixes. So 1 kilometer is 1,000 meters, which is equivalent to 10 to the third meters. Similarly, 1 milligram is 0.001 grams, which is the same as 10 to the minus 3 grams. So there's a whole bunch of prefixes out there. Some are more important than others. The ones that you should kind of try to not necessarily memorize, but you'll be using them enough that you'll memorize them whether you like them or not, are the ones I have in red boxes here. So a megagram would be 1 million grams, a kilogram would be 1,000 grams. We don't really talk about centigrams, but we use that for meters, so centimeters. 1 centimeter is 1/100th of a meter. A millimeter is 0.001 meters, etc. So it should at some point, not necessarily right now, but as you practice, it should get pretty quick and pretty easy for you to convert between kilograms and grams, milligrams and grams, etc. So we'll give you some practice working with those as well. So in order to use conversion factors, so for example, the conversion factor that 1 mile equals 1609.3 meters, what we can do is divide both sides by 1609.3. So if 1 mile equals 1609.3 meters, if we divide both sides by 1609.3 meters, sorry, there's a lot of background noise, I hope you can still hear me, that's going to equal 1. So for exactly the same reason that 2 divided by 2 equals 1, if you have two things that are equivalent on the top and bottom of your fraction, you're going to get 1. So that means that when we need to convert things, we often have this question of like, okay, I have 6 miles, I want to convert it to meters, do I need to multiply or divide by that conversion factor? And maybe you have some intuition for how big a meter and a mile is, so it might be easy for you to figure out here, but sometimes it's a little harder. So what we can do is take 6 miles times that conversion factor of 1609.3 meters divided by 1 mile. And then we can cancel things out. So if anything is ever in both the top and bottom of a fraction, you can cancel it out. So in this case, miles cancels out. And so we know that our final answer is in units of meters. And so if you had made a mistake and multiplied instead by 1 mile over 1609.3 meters, then you'd have miles twice on the top, and that wouldn't cancel out, so you know that's wrong. So every time I'm converting units, I still to this day write it out like this, because it's totally foolproof. If you always write it out such that you can cancel out the units that you want to go away, then you'll always get your answer in the right units. So just to give you some practice on this, here are a few practice questions that I'd like you to work on really quick in your Zoom breakout rooms. So yeah, if you can break into your groups and work on these. We're a little short on time, so you might not have time to finish all of them, and that's totally okay. Should we tell them like 2 minutes? Yeah, so we'll give you like 2 or 3 minutes. I don't know how much of a difference it would make. Yeah, probably not a lot.
It's one of those things where California just doesn't have insulation.
Okay, just about 30 more seconds. Okay, I'm just gonna, so it's okay if you haven't finished doing all of these conversions. The answers are as follows. So when we convert 2 miles to meters, we get 3,000 meters. I've rounded that. Katie will talk about why in a couple minutes. 86,400 seconds is 1 day. 5 times 10 to the 6 meters is 5,000, or 5 times 10 to the 3, that's the same thing, kilometers. And then the last one is 0.000005 kilograms is 5 milligrams. So that's a great example of, I would never want to write down that many zeros or keep track of numbers that small. So I convert to milligrams and use those prefixes. Okay, and then the last thing I wanted to talk about with units is derived units and dimensional analysis. So you might have noticed that I didn't list an SI unit of volume. And the reason for that is that volume is length cubed. So if you take a cube, it has sides of some length, and you can get the volume. So we don't need a specific SI unit of volume because we have a unit of length. So for example, a milliliter is a unit of volume, and that is equivalent to 1 centimeter cubed. So basically those SI units are the basic units that we build all other units out of. So milliliters are perfectly valid and useful units. They're just derived from length units. So similarly, density is a unit of mass divided by a unit of volume. And we can use units to actually do a lot of work for us to make sure that our work is correct. So for example, if force equals mass times acceleration, we can figure out what the units of force must be. So mass is in units of kilograms, and acceleration is in units of meters squared per second. And we need our units to cancel out on both sides. So that means that our units of acceleration must be kilograms, so mass, times meters squared per second, which is the unit of acceleration. And that is called a Newton. So that is the basic unit of force. So just as a similar example, this is the ideal gas law that you might or might not have seen before. If you haven't, that's totally okay. But what it says is that pressure times volume equals moles times this constant R times temperature. And what are the units of R? We can do the same thing. We can get R by itself. So we have pressure times volume divided by moles times temperature. And we just plug in the units of those things. So for example, Pascal is a unit of pressure. Again, it's okay if you didn't know that. Meters cubed is a unit of volume, moles, and Kelvin for temperature. So we can, without knowing what R really is or where it comes from, we know what its units are. So another thing that's really useful for is, and I do this all the time, if I derive an equation, so I do a lot of math with a lot of chemistry knowledge or whatever, and I come up with an equation, and I want a basic check of whether I'm wrong. So I've derived, for example, this equation that Q, which is energy, so it should be in unit of joules, equals mass times heat capacity, which you don't need to know what that means. It's in units of joules per Kelvin times kilogram, and then T's are both temperatures. And I can figure out whether that equation can be right or not. So I've given you 3 example equations here. And again, it's totally okay if you don't know what they mean. I made some of them up. And what I'm trying to show you is that without any knowledge of where these equations came from, all you know are what the variables are and what units there are. You can figure out whether this equation could be right or not. So I'm just going to give you just like 4-ish minutes to work on this, so you might not have time to finish all of them, and that's totally okay. But just kind of plug in some units here and see if your groups can get some intuition whether these equations make sense or not. The idea is that I've derived this equation, Q equals m times c times t2 minus t1, and I want to know, based on the units of all of these things, could that equation possibly be right? So I want Q to be in units of joules. If I plug in kilograms per mass, joules per Kelvin times kilogram for C, so that heat capacity, and Kelvin for temperature, do I get Q in units of joules? If yes, then this equation could be right, and if not, then the equation is definitely wrong. There's something wrong here. Okay if you don't have time to finish the last one, or even the second to last one. Just wanted you to get a little practice. Okay, so let's take about 30 seconds to come back together. Totally okay if you're not done. Okay, so I'm just gonna quickly go through the answers here. So for the first one, if I plug in kilograms for mass, joules per Kelvin times kilogram for heat capacity, and Kelvin for this temperature thing, I can cancel out the 2 kilograms with each other, I can cancel out the 2 kelvins with each other, and I get just joules. And that's what I wanted. I wanted my Q in units of joules, so that means that this equation could be right. It is not necessarily right, but we've ruled out at least one thing that could have told us that it was definitely wrong. So that one's right. Similarly with the next equation, we have coulombs times coulombs on the top. 4 and pi are both constants that have no units. And then for this permittivity thing, which it's okay if you don't know what that means, that's the beauty of this technique, is you don't need to know where these variables came from, you just need to know their units. So we have those units there, and then we have meters squared for the r in distance squared. When we do all our canceling out, we end up with joules per meter, but we wanted energy in units of joules. So that means that this can't be right. We don't know necessarily what went wrong, but we can very quickly know that we made a mistake somewhere and this equation has to be wrong. And then the last one, which I bet probably most of you didn't have time to get to, is a very similar concept. So we have this constant K in units of joules per Kelvin. We multiply that times units of Kelvin. And then we have this kilograms per meter times second, and we multiply it by meters squared per second. So your first instinct might be, well, this can't be right because I see joules on the top and I don't see joules anywhere else, so there's no way that the joules cancel out. But what you have to remember is that joules are a derived unit. So that means a joule is built up from other units. So a joule is equivalent to kilograms times meters squared divided by seconds squared. So when you make that substitution for joules, Now we can cancel out our kilograms, we can cancel out all our seconds, and we end up back in meters. So that one is a little bit trickier, and just to remind you that derived units can sometimes trip you up. So you have to get everything down into base units. So this equation is actually true. This is a real equation that I use in my research. So this is a good skill to have. And I want to remind you that on most tests you won't have access to a computer. However, there is an easy online way to get your computer to do this for you. So if you've never used Wolfram Alpha before, I'd highly recommend you take some time, not right now, but sometime before the semester starts, to play with it a little. So the website is wolframalpha.com. It's free. They're not paying me to advertise their service for them. You actually get a free account as a Berkeley student as well. So what you can do is type into the search bar anything you want. So you can have it solve an equation for X. It's really intuitive. So what I do all the time is, for example, for that equation we just solved, I have 1 joules per Kelvin, and I just make up numbers. And I have, so going back to this equation, where we have joules per Kelvin times Kelvin, I just assume some value of 1 joule per Kelvin and 300 Kelvin. And I plug that in, and it will do all the unit conversions for me, and then it will plug out an answer. And so what I see here is that answer is in units of meters. The number itself doesn't make sense because I made up the numbers that I was plugging in here. But I can tell that the unit is in meters, and I haven't had to manually do it myself. And it also will convert all those units for you. So you can type in, convert 2 meters to feet, and it will do that for you. Just a really useful tool. Don't get over-reliant on it, because on tests you'll have to be able to convert units and do dimensional analysis by yourself. So just wanted to point you to this tool that is probably going to be useful for you in the future. I use it all the time. Okay, great.
Yeah, so this program is actually how I made that plot with 1 over r. So there is a function where it'll just plot everything for you, which is really convenient, so you don't have to type everything in Excel. So it really can save a lot of time.
So you can just type in like y equals 3x plus 5, and it will make a plot for you.
Right. Yeah, so that's how you can do it and save yourself a lot of time throughout college. I definitely recommend checking this out and kind of playing with it to see all of the cool things it can do. It can do integration and all of those things that you will run into down the road when you start thinking more about calculus. Okay, so with the remaining time in class, I wanted to briefly discuss significant figures. So this is something that hopefully you guys have seen a bit before, but we just wanted to review some of the rules and why we use them. So as scientists, when we make a measurement, we need some way of conveying that there is uncertainty in this measurement. So one of the ways we do this is by taking into account how many of the numbers that we measure actually matter. So to do this, we count the number of significant digits in our measurements. So I first wanted to go over some of the rules for how you begin to determine if the number is significant or not. So the first general rule is that all non-zero numbers are significant. And then zeros between non-zero digits are significant. But then when we start thinking about some zeros at the beginning or end of numbers, it can start to get a bit more complicated. So for example, if you look at this number 0, 2, 3, 4, the first 0 actually is not a significant digit. We call that first 0 a leading 0, and in this case, it is not a significant number. So we only have 3 significant digits. Trailing zeros to the right of a decimal place are significant. So for example, if you have 0.400, that has 3 significant digits because you can count the 4, the 0, the first 0 after the 4, and the second 0 after the 4 all as significant digits. And then trailing zeros with a decimal point shown are significant. So for example, if you have the number 2000, that only has 1 significant digit. But as soon as you add a decimal place to the end of the 2000, now it has 4 significant digits. So what that does is it denotes that when you add that decimal point, that all of those zeros are significant. So these are some rules that unfortunately you're just going to have to memorize. And, hopefully they're somewhat intuitive, but you may just have to memorize them. Okay, so there's also some rules about how you do calculations while taking into account significant figures. So we're just going to go over some of these rules quickly and do a practice calculation on the side of the screen. So as I go over the rules, feel free to try to do this calculation if you'd like as I go over the example. So generally for addition and subtraction, the final answer is only as precise as the decimal position of the least precise value. So just keep in mind here for addition and subtraction, we're only considering the decimal portion of the number. So what you would want to do first is you'd want to count the number of significant figures and only the decimal portion of each number in the problem. So for example, if you're adding 2.45 plus 0.375, you would count the number of significant figures in the decimal of each. So for 2.45, you have 2 significant figures in the decimal place. And for 0.375, you have 3 decimal places that are significant. Then what you would want to do is you'd want to add and subtract these numbers like normal. It's always good to keep in mind that you want to round at the very, very end and not at the intermediate steps because that can introduce error. So then you would perform this calculation like normal and you'd get the following answer. But then in order to take into account the number of significant figures, you would want to round this to take into account the least amount of significant figures. So put in different words, we'd want to round the final answer such that the final answer has the same number of significant decimal points as the quantity with the least number of significant decimal points. So what that would mean that we need to round 2.825 such that it only has 2 decimal places. So that would give us 2.83. So hopefully that makes sense. I found that some of the best ways to kind of remember these rules is to just work through examples. And we will have a few different examples in your problem set too that's up on B courses. So definitely go through all of those and try to just get this into your head. So multiplication and division is a bit different. So for this one, you'd want to count the number of significant figures in each number. So for example, in 10.2, you have 3 significant figures. And in 0.4, you have 2 significant figures. So then just like we do for addition and subtraction, you'd want to multiply and divide the numbers like normal. So in this case, you would get 4.08. But then for multiplication and division, unlike addition and subtraction, you would want to round the final answer such that the final answer has the same number of significant figures as the quantity with the least number of significant figures. So that's a lot of words, but the important thing to take away is that in this case, you're counting the significant figures of the whole number, not just the decimal portion. So you would want to round 4.08 so that it only has 2 significant figures, just because our number with the least number of significant figures only had 2 significant figures. So in this case, you would round 4.08 to 4.1 because that has 2 significant figures. So we have about 5 minutes left. So if you could take 2 or 3 minutes to do this quick practice question to kind of reiterate some of these concepts, and then we'll come back together in about 3 minutes. And feel free to post more questions on this chat and definitely work together in your break rooms. Okay, so we'll give you about 1 more minute, and then we'll go over some of the answers, and then we'll pull you all back into the main Zoom room so that you can ask questions afterwards. Okay, great. For the sake of time, we're going to start going over the answers to these questions. So the first one is an addition and subtraction problem. So in this one, we would want to account for the number of significant figures in the decimal part of the number. So for this one, 100.0 has one significant decimal place, and 30.21 has two significant digits in the decimal part of the number. So we want to round off our final answer to one decimal place because that was the number of significant decimal points that was the least. So in this case, you would round 69.79 to 69.8. And then the second one, this is a multiplication problem, so you do want to follow that set of rules. So we have 0.333, so this has four significant figures. And then we have the slide, we have the number 20, which has one significant figure. So this is another good example where if we had 20.0, it would have three significant figures, but in this case we just have 20 and there is no decimal, so it only has one significant figure. So when we do this problem, we would want to round our answer such that the answer only had one significant digit. So in this case, you would round 6.666 to 7. Okay, so I saw in the chat that some of you wanted to go back to the significant figures slide. So we'll actually post all of these on to B courses. So if you go under the files section where there's like, course information, assignments, there's one folder that's also for lectures. So what we're going to start doing is we're going to be uploading lectures ahead of time so that you can take notes on the PowerPoint slides, and then we'll also upload the same slides that have answers to these problems after lecture so that you can always go back and review all the information and the different problems we did during class. Okay.
100.0 would not just be one sig fig. 100.0 has four sig figs, but when we're adding and subtracting, we care about the decimal points. So 100.0 has four significant figures, but it only has one digit after the decimal point. So that's where we get the 1, and that's what applies to addition and subtraction.
Right, yeah, so exactly. So the main thing to take away is that for addition and subtraction, you want to think about the number of significant digits in the decimal portion only. And then for multiplication and addition, you want to take multiplication and division, you want to take into account the number of significant digits in the entire number. Right.
Cool.
Okay.
So we want to, oh yeah, go ahead.
Yeah, so there were a few other quick concepts we wanted to cover, so I apologize that we're going a bit over. So we also, as scientists, want to consider how accurate and precise our measurements are. So colloquially, we often use these words interchangeably, but they actually have pretty different meanings. So precision is how close measurements of the same item are to each other. So for example, if you look at this figure, you see that all of the points on the target are all clustered really closely. So this is an example of a measurement that's very, very precise, because when you took this measurement repeatedly, you got the same value every single time. But a different concept is accuracy. So this is how close the measurement is to the true or accepted value. So this would be if you know that the correct answer is 1.000 gram and you kept getting 0.8 gram over and over again, you know that you weren't very accurate. So it's important to keep this in mind in scientific measurements. And then one other thing you want to consider is what your sources of error are. So there are sort of sources of error that are going to be inherent to every measurement you do as a scientist. So there are two main types. One is random error. So these are errors that vary at random. And then there's also systematic errors. So these are predictable errors that affect every measurement in the same way. So a good example of a systematic error is if you're trying to repeatedly take the mass of a compound, but you forgot to zero the scale. So that you had this sort of offset in every single measurement, but it affected them all in the same way. So these are sort of some basic definitions that we had to go over very quickly because we're short on time, but feel free to ask us about this in the Zoom call afterwards. Okay. So that is the end of lecture today. So I see that there's some questions popping up in the chat. So if you still have questions and we haven't answered them, please stay in the Zoom room for our office hours. I also realize that a lot of you weren't familiar with limits, which we discussed today. So what I'll do is I'll send out a short summary of what that means mathematically on B courses. Our goal here is to really start to get you thinking about some of these mathematical concepts and how they relate to chemistry. So we really just want you to sort of be able to look at graphs and see what sort of directions these things are moving in. We'll send out a review of that on B courses later today.
Also, just real quick, we would really love to be able to start right at 10:40 on Berkeley time. So it really helps us a lot if you're able to make a Berkeley Zoom account. We know that not everyone is able to, but if you can, please try. And then also please try to log into the Zoom and the YouTube stream a couple minutes early so that we can really get started right at 10:40. That would really help us out a lot.
Yeah, and one last quick thing is if you have issues with any other students in your breakout room, please let us know. We want to make sure that everyone has a good experience and we expect everyone to be behaving professionally. So that is something we would definitely like to know. Please email us if that's the case.
Yeah, and also just generally anything we can help you with, we're always happy to help. Okay, so I'm going to end the YouTube live stream once the lag catches up, so I'll end it in 20 seconds, and then we will be on the Zoom if you have more questions you want to discuss with